Unit 3, Worksheet 1, Development of Accelerated Motion Representations. Problem 1. The data to the right are for a wheel rolling from rest down an incline. Using the position time data given in the data table, plot the position versus time graph. Now this is going to be a position versus time graph. So the first thing I'm going to do is add a title. Position versus time. Now, when that title is position versus time, that means our position goes on the y-axis for our dependent variable. So the variable gets written out, or you can use the abbreviation. For horizontal position, it would be the variable x. In parentheses is how we're going to measure this. From the table, this looks like it will be in cm for centimeters. And it goes from 0 centimeters all the way up to 180 centimeters. Now, this graph has 40 boxes going up and down on the y-axis. So if I'm going to say I go up to say 200 centimeters, if I have 40 boxes to distribute that evenly, that would be 5 centimeters a box. Starting off at 0, and I'm just going to skip every other one to save myself some writing. So every 2 boxes will be 10 centimeters. 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, and 200. Even though I'm only going up to a maximum position of 180 centimeters, this right up here won't be a whole lot of empty space, so it's going to be okay to leave that blank. The whole reason we try to use up as much space as possible is to make the graph as easy to read as possible, which is why it's okay to have a little bit of blank space from time to time. Now, on my x-axis, that's going to be my independent variable, which in this case will be time. So I'm going to write time underneath my x-axis, and in parentheses is how we measure time, which will be in seconds. There are 8 boxes going left to right, but I only go up to 6 seconds. Now, same thing with our position axes. It's okay to have a little bit of blank space to make it easier to read. So I'm just going up by increments of 1. 1, 2, 3, 4, 5, 6, 7, and 8. Even though I won't be using my seconds over here, I can have a little bit of blank space just to make my graph super easy to read. Now what I'm going to see is I'm now going to plot my points. My first point, a time of 0 seconds and a position of 0 centimeters. So right here is going to be my first data point. At 1 second, it's going to be 5 centimeters. 2 seconds, it's going to be at 20. 3 seconds will be 45. 4 seconds will be 80. 5 seconds will be 125. And 6 seconds is going to be 180. Now, I am not really going to be able to have a line of best fit that's going to best fit all of my data. Now this is going to look more like our graph that we saw from the lab, where it's going to be the position drastically increases over time, where the slope between those 2 points constantly gets bigger and bigger. What this means is our position is going to be directly proportional to the square of time. Now that our data is plotted, we can move on to the next few problems in order to make use of this graph. Now this is something that you'll have written down in your lab notebook, but for the purpose of this video, it's just going to be on the next page in the presentation that I'm going to have here. I'll constantly come back to this graph to use it. Problem 2. What is the significance of the slope of a position versus time graph? Well, this is actually really something that we can start thinking about that we learned back in Unit 2, which was constant velocity. The slope of a position versus time graph tells us the velocity. So we could figure out the velocity between any 2 points and say that, well, it looks more or less like it's going to be an uniform velocity between each of these points. Although, realistically, we know it should probably be changing, seeing as the overall velocity is going to be changing. But that's what the slope tells us. It's going to be the velocity. But if we just connect the first and last data points, it's not really telling us the real velocity at each period of time that the wheel is rolling. Same as if we had just a line of best fit for those data, it wouldn't do a really good job of representing the data very well. But in general, the significance of the slope of a position versus time graph is that the slope of a position versus time graph tells us the velocity. Question 3. What is happening to the slope of your position versus time graph as time goes on? Well, it looks like the slope is constantly going to be increasing. So we can say the slope is constantly increasing. Now we can also say what the physical real-world meaning is, which is the velocity is constantly increasing. Now, if we remember from problem 2 that the slope of a position versus time graph tells us the velocity, and from number 3 that the slope or the velocity is constantly increasing, then answering number 4 will be relatively simple. Question 4. Explain what your answers to questions 2 and 3 tell you about the motion of the wheel. As long as we are constantly answering these in real-world terms, we can explain in real-world terms that the motion of the wheel is that it is constantly increasing in velocity. So, for question number 5, on the position versus time graph, draw a line which connects the point at a time of 0 seconds to a time of 6 seconds. Now this is where we will need to revisit our graph. We're drawing a line from the point at time 0 and the point at time 6. So time 0 is going to be right here. Time 6 is going to be up here. So if I have a single line that is going to be connecting these, that's what the line would look like. Question 6. Calculate the slope of this line in the space below. Explain what the slope of this line tells you about the motion of the wheel. So I'm actually going to solve for that slope up on the graph itself, just that way we can see the slope of the line itself, and there's going to be some space for my calculations. But this is something that you should write in your lab notebook on the appropriate page. So we're going to go with, this is going to be our line over here. I'm going to do it in red. So for problem number 6, the slope of our line, which is going to be the same thing as our velocity, we can calculate that by going with our y2 minus y1 over x2 minus x1, or the rise over the run. However, if we want to keep this in real-world terms, we can say that our velocity is going to be equal to our seconds position minus our initial position over our second time minus our first time. Our second position is going to be 180 centimeters. Our second time is 6 seconds. Our first position was 0 centimeters, and our first time was 0 seconds. So our velocity from 0 to 6 seconds, it's going to be 180 centimeters every 6 seconds. And just by good form, we can simplify that down to the number of centimeters every 1 second. So we'll need a calculator in order to determine that. 180 divided by 6. That's going to be 30 centimeters every 1 second. This is going to be our answer for problem number 6, which I'm also going to write down in the appropriate area on the page. So my velocity in this region was 30 centimeters every 1 second. We had a change in position of positive 30 centimeters every 1 second. Question 7. On the position versus time graph, draw a line which connects the point at a time of 2 seconds to the point at a time of 4 seconds. So we're going to go from a time of 2 seconds to a time of 4 seconds. I'm just going to change the color of my line real quick, just to make it a little bit easier for us to see. Yeah, let's go with green for this one. So 2 to 4. So for question 8, calculate the slope of this line in the space below. Explain what the slope of this line tells you about the motion of the wheel. So for question number 8, it's going to be the same thing where we can calculate our velocity by looking at that change in position over our change in our period of time. So our second position here is 80 centimeters. Our second time is going to be 4 seconds. Our starting time in this region was 2 seconds, and our starting position in this region was 20 centimeters. So our velocity in this region, 60 centimeters every 2 seconds, or 30 centimeters every 1 second. Going to write that in the area below. Our velocity in this region is 30 centimeters every 1 second. So I'm going to explain what the slope of this line tells you about the motion of the wheel, which is something that I forgot to do for problem number 8, which is what I'll go back to do in just 1 sec. But right now, for problem number 8, the slope of this line from a time of 2 seconds to a time of 4 seconds tells us the average velocity in that region. Now, that's going to be a very similar explanation to what we have for problem number 6. Explain what the slope of this line tells you about the motion of the wheel. The slope of the line from a time of 0 seconds to a time of 6 seconds is going to tell us the velocity in the entire time interval. So for the last few problems, problem number 9. On the position versus time graph, draw a line tangent to the graph at 3.0 seconds. So that word tangent right there, that means it's going to touch our graph at only one point. So it's going to be a line that is tangent or just touching a single point on our line. So at 3 seconds, what we can look for. So 3 seconds. So at this point, we're going to look for a line that is tangent to that point. So I'm going to try to show it that where it's only touching a single point, which can be a little challenging to do. This is why it's a good idea to have a straight edge to help you out. Whoa. Okay, zooming in, if you have the ability to do that, would be helpful. Okay. So at that point, it's going to be a line that is just barely touching the single point on our curve and really no other point. If we continue this line all the way until the end of time, going up, it will never reconnect with our curve. Same as if we went backwards in time, it would never touch our curve. So, question 10, calculate the slope of this line in the space below and explain what the slope of this line tells you about the motion of the wheel. So going back to my graph, I'm going to solve for my velocity right here. Now, unlike the previous ones where we could actually use the starting position and final position in order to calculate that change in position over the change in time, which was our velocity, this one we're going to need to pick points on the tangent line that we know. One point that I would recommend we do is the point that we are given. So one of the points that we can know is we know at 3 seconds, we have a position of 45 meters. Now we just need to find a point either before or after it that we know for a fact what that could be. One that I'm seeing is pretty close is going to be right up here. That looks like it's going to be at 5 seconds, so a bigger time. And it looks like it'll be a position of exactly 100 meters. So using that, the slope of this line, or the velocity at 3 seconds, is going to be 55 meters every 2 seconds, or 27.5 meters every 1 second. And this is going to be for problem number 10. So, this slope of the line, the slope tells us the velocity at 3.0 seconds. Now, because we're seeing the velocity is changing, well, over time, one thing that we can try to figure out is that if we want to look at every single time on our graph, we could figure out what each of those velocities really means. And in order to do that, that's when we need to use the tangent line. Question 11. Compare the slopes you have calculated in questions 6, 8, and 10. Explain the results of your comparison. So, for question number 6, our slope or our velocity was 30 centimeters every 1 second. For question number 8, our velocity was 30 centimeters every 1 second. And for question number 10, our velocity, that slope of that line, was 30. Nope, that one was not 30. Just the other two were. That one was going to be 27.5 centimeters every 1 second. So explaining the results of your comparison. One thing that we can say is that for region number 6, we can calculate the average velocity in the middle region of our graph, which is 30 centimeters for every 1 second. For question number 8, we can also compare the average velocity over the entire time region of our graph. And for question number 10, we can calculate our instantaneous velocity, the velocity at that one exact time interval at 3 seconds. And we can see that they're all really similar to each other. So what we can really see is if we want to find the velocity or the average velocity of the entire graph, the average velocity can be calculated from the initial and final positions, a middle region of the graph, or the exact middle point. Now, the last question, question number 12. Consider an object accelerates uniformly. If you were to calculate the average speed of the object for a given interval of time, would the object ever be traveling with an instantaneous speed equal to that average speed? If so, when? Explain. So, well, one thing that we can see is if we look back at problem number 11, our instantaneous velocity, or our instantaneous speed, if we were just focusing on how fast it's traveling instead of the direction, is going to have the exact same number at, well, for our instantaneous at the exact halfway point between our starting time and our final time. That middle time is going to have the exact same speed as the average speed along the whole time interval. So the average speed and instantaneous speed are the same at the halfway time, t of 1/2, in the entire time interval. Now, if we wanted to give a very, very thorough explanation, we would go back through every single problem we did in this first part of worksheet 1, where we look back at problem 11, where we compare all of those velocities. We can look back at problem number 10, where we can see we have our instantaneous velocity very, very similar to our average velocity across the entire time region, as well as to the intermediate time region. We can see for this problem, problem number 8 was going to be the one just from that intermediate time region, and from problem 6, the entire time region. So at this point, our graph should be marked up with our data points, the axes labels, the title, as well as at least 3 lines. The line connecting our position at 0 meters and at 180 meters. Our tangent line, this purple one, and our line, that's the green one, that is connecting our 2 and 4 seconds.